Okay, so Lab 7, Problem 3. Now we have a cart that's attached to two different springs. It can be displaced from its equilibrium position, and it's going to oscillate back and forth. So here I said that x equals 0 at the left-hand side and x equals L at the right-hand side. I have defined x equals x equilibrium, which means it's at the point where the center of the car is at, well, when the center of the car is at this point, the force from the spring K is equivalent to the force from the spring constant K2. So force 1 is equal to force 2. And then I have these other variables right here, which basically just explain, well, when the first spring is at this position, it's at its relaxed point, and then when the second spring is at this position, it's at this relaxed point. So the two springs don't necessarily apply zero force at the equilibrium position. Rather, at the equilibrium position, the force that they apply is the exact same. So when the cart is at the equilibrium position, the net force is 0. So we draw a free body diagram on the cart, and we say that these two forces, F1 at the equilibrium position and F2 at the equilibrium position, are equivalent. So we can say that the spring force is equal to K times some distance from where the spring would be at its relaxed position. So in this case, I'm saying that it's x1 relaxed minus the equilibrium position. Now you should note that this will be a negative number because x1r is lower or closer to the 0 point of the x-axis than x equilibrium is. So when you do a smaller number minus a bigger number, it's going to be a negative number. Hence, this direction is in the negative x direction. So I realize that it's kind of confusing when you have f equals negative kx and when you're trying to relate it with two different x positions. So one of the things you should probably do first is actually draw where the forces are going. Then it's a little bit easier to make sure that this is correct. So I didn't really think of it in terms of, well, f equals minus kx. I thought of it in terms of, well, the direction is being pointed this way, so I need a negative number as the force. And then so here, notice that x2 at the rest position right here is actually further away from the origin, so it's going to have a higher value than the x at the equilibrium position, which means that this is going to be positive, and we see here that the force is in the positive direction. So this is pretty much because both strings I'm saying are stretched, so the force is going to want them to pull it towards the equilibrium position. And then finally, the definition of the equilibrium position is that the sum of the forces equals 0. So if you add these two forces together, they'd equal 0. And therefore, the second force at equilibrium is equal to minus the first force at equilibrium. So in order to actually solve this problem, we have to generalize the coordinates or the forces such that it can work if the system is not in equilibrium. So if the cart is displaced a distance delta x, now all of a sudden we have a situation where the force from the first spring is not equal to the force from the second spring. And there's going to be a net force and a net acceleration on the system. Now what you'll find in this case is that the spring force is actually a restoring force, which makes the system want to go back to the equilibrium position. So the net force is always going to be directed towards the equilibrium position. Whether the cart's over here, then the force is going to be this way, or in this case, when the cart's over here, then the force is to the left. So let's say it's been displaced a distance delta x, so k1 is going to be x1r, which is the rest point of the first spring, minus xeq plus delta x. So now note that there's a xeq plus delta x means that it's further away from the x1 rest, which means that this force is actually bigger. Now contrast that to this case, we have x2r minus xeq plus delta x. So remember, it's the same, it looks like it's the same expression, but here, if you look at the diagram, it's clear that actually the center of the cart, which is where I'm like defining where x is actually closer to being here. So that means that the second force is actually lower than F1 is at this point, and it's also lower than it was at the beginning. So if we drew a free body diagram, notice that I have F1, the force vector, way longer than F2. So the net force is going to be in the left direction, and it wants to get back to the equilibrium position. So now I'm writing the sum of the forces in the x direction as F1 plus F2. So we just have our expressions and then we plug them in here. This should be a plus sign. And then so the other thing that you should know, so again, this should be a plus. So the other thing that you should note is delta x can be negative, so it can be this way, which would actually mean that F2 would be larger than F1, and it would want to get towards the equilibrium position again. So we can factor all these out, and let me see, did I mess up because I had the negatives? No, okay. So when I foiled this negative in, I did have the correct thing here. So pretend that this is positive, it would still be K2 times delta x, but the negative sign in front, because if you had this as negative and this is negative, the negative signs are canceled out. So this would be a plus, but I did not do that, so I guess I made two canceling mistakes. Anyway, so we factored all these out and we get all of this. And so the force of the spring at the equilibrium position is K1 X1R minus K1 XEQ. So notice that this is these two terms. This is the force 1. And then the force of the second one at equilibrium is actually these two terms. So if we and remember F1 equals minus F2 at equilibrium. So I'm just replacing those two terms, which are equivalent to F1 at equilibrium and F2 at equilibrium, in this equation. So now we've placed those two terms in for here and those two terms in for here. So remember, F1 at equilibrium equals negative F2 at equilibrium. So this should be a negative sign right here because I replaced F2 with negative F1, so this is a negative sign. And since this is a negative sign and this is a positive sign, these two terms would cancel each other out, and we're just left with negative K1 delta x and negative K2 delta x. Okay, so that means that the sum of the forces in the x direction equals mass times acceleration in the x direction, and that's going to be K1 times delta x minus K2 times delta x. And so let's say that delta x is just x minus the equilibrium, minus the x at where the equilibrium was. So that's just saying that we can say that x is any position at any point in time, and then if we subtract that position from the equilibrium position, that's delta x. So you can factor out the delta x, and then that's going to leave you with minus K1 plus K2, and then replace the acceleration with d squared x dt. So you end up, okay, and then, so there's one more thing that I'm going to do. So XEQ is just a point on the x-axis. It just represents a number. So we can shift the origin of our x-axis so that at x equilibrium, we can say that at 0. So that gets rid of this part. And then we're just left with d squared x dt equals negative K1 K2 times x, where this x is the position away from the equilibrium point. So if you look at this equation, it's very similar to what we did in Lab 7 problem 1, where we had d squared x dt of y of t equals negative k times y of t. So we're going to use the same procedures that I outlined in that video to solve it. And I'm going to skip over them in this video, but you should try to see if you can use the same procedures to get the answer that I got. So in this case, we just have some different constants. We have K1 plus K2 instead of K. That's really the only difference. So when we do our, let's guess that the solution is a sine omega t, take the derivative a couple times, and then, oh, we see that when we do that, we get this relationship. We can solve and find that omega is k1 plus k2 over m, and then obtain the frequency. So now it's pretty similar to what we did in the first problem, except now that there are two spring constants. So as you might expect, the frequency is in terms of those two spring constants. One thing that you might want to consider, these two spring constants don't have to be the same. We solved it for a general case where this could be any spring constant. So pretty cool.